Okay, worksheet 16. Just like the last one, there is a circuit that I would have built in class and put a fault in. Obviously, I can't do that in the virtual world that we live in now. So I can tell you what my fault values are. V1 to 0 is 8 volts for this circuit. And V2 to 0 is 2.7 for the faulted circuit. So we'll put a V up here by the 8 because I always want you to put a unit in there. Alright, so that is the first three. Another faulted circuit. Tell me what the fault is in the circuit. 4 and 5. Observer have described a DC waveform on the oscilloscope. Then using an oscilloscope, set a DC voltage equal to your birth month. So can't simulate that so much. I can show it to you. So what I've done in LT Spice is I've set up a circuit with a voltmeter going across a resistor. Resistor doesn't matter. And I'm using something called transient analysis. And when I use transient analysis, what I get out is what you would see on an oscilloscope. So typically on the oscilloscope, you have tick marks, and you actually have a grid across the screen. In LT Spice, the little tick marks are over here on the side. And each of the tick marks will be worth so many volts. So the intention was to set up the grid, and I'm going to look into that, see if I can do it. Set up a grid across there so you can actually count what happens. I was born in November, so I set up an 11 volt DC source, as you can see here in Spice. And this is what it would look like on the oscilloscope. It's a flat line, about 11 volts level. Normally, your 0 on the oscilloscope is in the middle, so you've got negative voltages and positive voltages. And when we get into an AC source, you'll see why that it swings from into positive and negative territory. I can set the voltage of the window, the voltage range of my window. I set it from -20 to 20. On the oscilloscope, when you turn knobs and stuff like that, you're basically either changing your voltage up and down, which would be the vertical axes, or you're changing the time, which is the horizontal axes. So, and I've got this one set up 0 to 5 seconds. You can't see the 5 over there on the end, but that's okay. That's what a DC looks like in Spice. Now if I go back to the right worksheet. Okay. So I would have you on the bench, set a DC voltage level equal to your birth month. This gets out a scope probe, sets it up to your DC voltage source that you're used to, and then that's all you look for. For 6 to 9, observer have described an AC waveform on the trainer or the oscilloscope. So to do that, I'm going to go in and modify my Spice circuit, and instead of a DC source, I'm going to go into advanced, and I want it to be a sine wave, and I want my amplitude to be 10 volts. I don't want any DC offset. I want my frequency to be, let's see, I don't know if I want to do that. I can do that. So let's make my frequency 2. Whoops. I got to click in the box 2. Okay. Time delay. Most things you can leave blank. Eventually we will be setting this up. For right now, I'm just wanting you to see what the result is and what it would look like potentially on the oscilloscope. Okay, so I'm going to click OK. And I'm going to tell it to rerun my simulation. And what you see now is I've got my signal is now a sine wave. Now it changed the range on me automatically, and Spice will do that. So if I right mouse click on it, I can make the range whatever I want. So if I want to go back to 20 and 20, I can do that. And I want my tick marks to be every 5 volts. That would be more like it. There we go. So that's what you would see on the oscilloscope if you had it set up range-wise for 20 volts. And what you see is that I have a 10-volt peak. So my amplitude is my distance between 0 and 10. Amplitude is the highest point of the waveform. And then what you see is my amplitude swings from positive down to negative 10. Okay? And you see that this waveform repeats. Okay, and that's important too, because as we start to look at AC waveforms and we start to try and understand what they look like and everything else, then we will remember these facts. So let's go back to this part. All right. So, concepts. This is always true. So once you get it, you got it. All right. In this class, people will talk about a voltage PP. And what that means is voltage from peak to peak. And when they talk about a peak-to-peak voltage, they're talking about from the positive peak to the negative peak. So, back in Spice, what is my peak-to-peak voltage of that waveform? Well, if I measure from this point, the top of one peak to the bottom of the other peak, how far have I gone voltage-wise? And what you see is I'm going from positive 10 down to negative 10, so I'm going a distance of 20 volts. So your peak-to-peak voltage, even though it swings from a positive 10 to a minus 10, my peak-to-peak voltage here would be listed as 20 volts. Okay, 20 volts. All right, what is my peak voltage? And it's important to know what the concept means. So what you'll see is, going forward, is somebody will tell you a voltage in peak to peak, and now you know what that means. Where's the top swing? Where's the minus swing? Alternatively, they can tell you what the peak voltage is. And so what is the peak voltage of this waveform? So my peak voltage is measured from 0. So my 0 to my peak is how far. And in this case, it's 10 volts. But on any sine wave, if you know how far up it goes, you can tell me what the peak voltage is, and now you can tell me what the peak-to-peak voltage is, and you can tell me what the relationship between the peak voltage and the peak-to-peak voltage is. Okay? And the reason we're doing this is because everybody needs to be on the same page electronically. Everybody needs to be on the same page in terms of when you ask for something. Later in electronics classes, oftentimes the voltage peak to peak or the voltage peak is used. The other information you can get from a waveform is something called the period. So how do I measure the period of this waveform? Well, now the period of the waveform has to do with how often it repeats. So I'm right here at 0 seconds. I'm right at 0. And I'm going in the positive direction after 0. I'm also at 0 here, but I'm going in the negative direction after that 0. So what I'm looking for is the point where it repeats. So if I come over here to this one, I'm at 0 here, and I'm going in the positive direction. So what you're trying to do is break this down into one, what we call cycle. So if I start here and I do one cycle, I end back up at 0. And so then if I do another cycle, I can do another cycle, end back up at 0. Another cycle, and I can keep going. So the period of a waveform is the time being your horizontal axis on an oscilloscope in most cases, that it takes to do one complete cycle. Boom. Now the way I set this waveform up, it's pretty easy. I do have some photos of waveforms I've used in the past, and I will probably recycle them into this class. So your period will be, you will figure out how much. So my period for this waveform goes from 0 to 0.5 seconds. So my period is 0.5 seconds. You always need to get your period into a value of seconds. A lot of times in a signal that you typically see in AC, you will be in milliseconds or microseconds. And so that's why we started out with the conversions, because we want to get back to seconds. Because if we get back to seconds, then what we'll find out is our frequency of the waveform is 1 over the period. Okay, so in my example here, my 10 volts peak to peak, 20 volts peak to peak, 10 volts peak, a period of 0.5 seconds. And this is all coming off what the oscilloscope would be showing us. If I took a multimeter into my circuit and I put it on voltage and I measured my voltage across my resistor or coming out of my waveform or coming out of my voltage source, it wouldn't matter, then my meter is going to measure something called the root mean squared, or the RMS value. I got too many documents open. Okay, so measure the voltage value with a multimeter and compare that value to the peak waveform seen. What I would see on this waveform is that my multimeter or my voltmeter would read about 7.1 volts for the waveform shown. Okay, and that is my RMS. So now I've got 3 different voltage types I have to keep up with. I've got my voltage, I've got my peak voltage, and I've got my peak to peak voltage, and they all have specific meanings. You can't mix and match them. Now if somebody gives you the peak, you know what the peak to peak is, you just double it. And if somebody gives you the peak and you know what kind of waveform it is, which is a sine wave in this case, you can get to the RMS. That's going to come up a little bit later. The other thing you can do is determine the frequency of the waveform. Now, most multimeters, you can actually get them to read frequency directly, so you can get that. But if you know the period, then the frequency is 1 divided by the period, and the period has to be in seconds. So for my example, if I took 1 and I divided by 0.5 seconds, which was our period, I would come up with a frequency of 2, which would be hertz. Okay. And then I could check the frequency with my multimeter, and it would, if it reads frequency directly, and all the bench meters do, it's a button you push, you would see that you have a 2 volt, a 2 hertz signal, if that's what we were looking at. I usually use about 60 hertz because that's the most common, but I would have to change my range, and I think this is a little bit easier starting out. Okay, oscilloscopes also allow you to check their calibration. So within an oscilloscope itself, it has a little function generator that generates a waveform that you can look at on just about every oscilloscope I've seen. And it basically is a square wave, and it tells you on the oscilloscope what the level of that square wave should be and what the frequency of that square wave should be. I'll probably do some square waves, but a little harder to do in LT Spice. Nothing's impossible, some things are just more difficult. Okay, so what I'm going to do is I'm going to find my pictures, or I'm going to take some new ones, and I'm going to post pictures for you to look at, period, for you to come up with the voltage level and the frequency. You can give me the voltage level in anything you want. So if you're looking at an oscilloscope, you'll be telling me what it is in terms of either peak voltage or peak-to-peak voltage. Now that you know what it is, frequency, you'll have to look for how long it takes to repeat, and then you will tell me what the frequency of the waveform is. Now, 13 is redundant question. How does period relate to frequency? Well, I just told you, and I don't know why frequency is 1 over period, or period, which is usually a capital T, is 1 over frequency. So they are just reciprocals of each other. The period will always be in seconds. The frequency will always be in hertz. So if you've got one, you can get the other very easily. It's just the inverse key, or the 1 over key, or however your calculator does it, or however you want to do it in Scilab or whatever. Okay. Now, I said earlier about your meter value is reading something called an RMS value. Now, nobody writes RMS. So what you typically see when you see a RMS value is you'll just get a V. If it's a V without anything, it's RMS. If it's a VP, then they mean peak voltage, which you can get off the oscilloscope directly. And if it's VPP, then they're looking for peak voltage. But your meter will always, your multimeter, bench multimeter, will always read the RMS value. Okay? Alrighty. So what's the relationship? Well, I told you very carefully, and I was very careful with my words for a reason, that for a sine wave, if the 10 volt peak sine wave would read about 7.1 volts RMS. From a mathematical standpoint, if I was to make everything positive, and I would do that by squaring, that's part of the root mean squared word, right? RMS, the last word is squared. So if I square all my negative voltages, what do I wind up with? I wind up with positive. And then I'm going to take the square root of it. So basically I would make everything positive. And so mathematically what we're doing is we're looking for an average or a mean. So if I make all these positive going to 10, 0 to 10, 0 to 10, 0 to 10, 0 to 10, and then I look for the mean of a sine wave, it's going to come out to be about 71%, or the square root of 2 over 2, if you want to be a math purist. But that will always be the case. It'll wind up being about 70% of the peak. Now, that is only for a sine wave. So you've got to keep those straight. So what's the relationship between the peak voltage of a sine wave and the RMS value? So my peak, 0.71, and I like to use 0.71 because it's easy to remember. You can do the square root of 2 over 2. It's like a lot of things we do in class. let's see. Yeah. It's like a lot of things we do in class. We're just looking to get in the ballpark. We're not looking for perfect, exact answers. We just want to predict how a circuit's going to behave, and then if we can predict how it behaves, then we can go in and work on it and measure it, troubleshoot it, and everything else. We know there's variations. Okay, so this is for a sine wave, 0.71. The important thing to remember, if you can't remember which way to go, is that your peak is always going to be bigger than your RMS. Always. So what you could do is say V divided by 0.71 equals your VP if you're going the other way. And what you would see on the bench if we were able to meet and you were measuring an AC waveform on a bench, you would see that that holds up pretty well for a sine wave. Okay. Now imagine what would happen if I had a triangle wave. I still have my V, which is my RMS for a triangle wave. I still have my VP, which is the peak value it gets to. And I can still talk about my VPP, which is the peak-to-peak value of my triangle wave. But if I have a triangle wave instead of a sine wave, here, what you would see is it's not as rounded, it's more pointed, there's a little bit less. So then what would my root mean square average be? And so if you remember from back in the day, what was the area of a triangle? And the area of a triangle was worked out to be 1/2 times base times height. So basically the area of a triangle is, if I made a square out of a triangle and I came up with its area, it would be half the square. 1/2 base times height. Well, that's excellent news for us, because in terms of a triangle, my relationship between peak and VP is 0.5, or 1/2. 0.5 times VP, I'll go ahead and put in the times. I can't stretch my fingers that far. There you go. So just like in the sine wave, my relationship, my RMS value will always be lower, but my factor is different because I have a triangle wave versus a sine wave. And I can do what I did over here. I can say V divided by 0.5. Whoops. 0.5 equals VP. Okay, cap. Fine. There we go. Okay. So this only applies when you're going between peak and RMS. The relationship between peak and peak-to-peak is going to stay the same whether I'm with a sine wave or a triangle wave. And now I've got my square wave. So now I've got a square wave, and eventually I'll show you one, or it will be as part of that part of the ones I'm gonna attach. Square wave. So I can still talk about its peak voltage, its peak-to-peak voltage, and its RMS voltage. What do you think the RMS and the peak voltage relationship for a square wave would be if, instead of this sine wave, you had pulses that went all the way up, straight across, back down? Down, up. So what you would see is if I got rid of the negatives and switched them all positive, I'd essentially have a flat line up here, or my average, my RMS average, would be the same as my peak value. So I can still talk about voltage, voltage peak, and voltage peak to peak. And what you notice on a square wave is that it's the easiest of them all. My VP equals my V. In other words, my RMS equals my peak, or my peak equals my RMS for a square wave only. For a triangle wave, it's half. For a sine wave, it's 71%, or square root of 2 over 2. Okay? So that is the beginning of the relationship. Now I'm going to ask you questions about this the rest of the semester, because I have a lot of people in the past have a hard time with this frequency and period thing too. And I want you to get in the habit. I want you to train your eyes. When you see a problem, do they give me the voltage in peak to peak? And I know what that means. Do they give me the voltage in peak? I know what that means. And do they give me the voltage in V? I know what that means. If you can keep those straight and then realize that depending on the wave type, the relationship between peak and voltage is different, you'll do great. And the nice thing is it's not going to change on you. So once you get this straight in your mind, you're in good shape. 17 through 20, this would be something I'd have you set up in the classroom. Obviously you can't do it. We're going to have to omit those for the purposes of grading. So anyway, that should help you with this worksheet. Let's see, waveforms. Okay, so 10, 11, and 12, worksheet 16. I'm going to put a waveform out there, and then I will go in there and let you tell me. I need a voltage level and I need a frequency. When you look at a picture, I don't care what voltage level you give me because I didn't ask for it in a specific form. So if you give me peak voltage, make sure you write it down as peak voltage. If you give me the peak to peak voltage, make sure you say it's peak to peak. If you want to calculate the RMS voltage and just put down V, then you better be giving me the RMS value for that waveform, which you can't see directly. And then the frequency, you'll have to come up with a period. You'll have to convert whatever that period is to seconds, invert it, and then you will be able to tell me what the frequency is. And my frequency unit is always going to be hertz. So let's put that in there. Frequency is in hertz. If it's a big number, then you can talk about kilohertz, megahertz, whatever. But there we go. Okay, so I need a 10, 11, or 12. And I need to put a picture in there. I think I have them in the last class. I just got to move them in Blackboard. But they should show up about the time you get to this video, and they should be around the video. Anyway, thanks for watching, and good luck.